This is a crash course in all of leaving cert complex numbers. I'll start by explaining what it means when you see the letter I in an equation. To do this, I'm going to square 3 and minus 3. 3 squared, I get 9, and minus 3 squared, that's like minus 3 times minus 3, is also 9. And now I can see that the square root of 9 could be positive or negative 3, and I write that like this. But if anything, whether positive or negative, will give me a positive number when squared, then how do I find the square root of a negative number? And this is where imaginary numbers come in, where the letter I is just equal to the number which is the square root of minus 1. With this, I can solve for the square root of a minus number. I'll just go ahead and work out this example here. So the square root of minus 9 is going to be the same thing as the square root of 9 times minus 1, which again is the square root of 9 times the square root of minus 1. And now I can see that I've simplified this sufficiently that I know what each of these terms are. And this gives me that the square root of minus 9 is, taking that the square root of 9 is positive or negative 3, times the square root of minus 1, which if we look here, is I. And that's how I write the square root of a minus number. Following this, a complex number will come in the form z is equal to a plus bi, where a is a real number and b is the coefficient of I. So this here is called the real part of a complex number, and this is called the imaginary part. A complex number, if I sub in some actual values for a and b, will look something like this. Maybe it's 2 plus 3i. And this is just the number that is equal to 2 plus 3 times the square root of minus 1. You can perform operations like addition and subtraction on a complex number. Here I'm given z1 is equal to 1 plus I and z2 is equal to 6 plus 2i. And I'm asked to find z1 plus z2. For this, the rule that I follow is I add the real parts and I add the imaginary parts separately. So z1 plus z2 is equal to 1 plus 6, that's both the real parts, plus I plus 2i. And that's the imaginary parts with this I here. So if I simplify, we can see that this is 1 plus 6, 7, plus 1i plus 2i is 3i. The same thing goes for subtraction. Here I'm asked for z2 minus z1, so I'm going to take away the real parts of z1 from the real parts of z2, and then I'm going to take away the imaginary parts of z1 from the imaginary parts of z2. So this is the same as 6 minus 1 plus 2i minus I, which gives me 5 plus I. Multiplication for complex numbers works the same as in regular algebra, but there is one thing that I need to look out for, and I'll show you here in the example. So z1 I said was 1 plus I, and z2 was 6 plus 2i. And to expand these brackets, I use the distributive law, so it's the first term of this bracket times the first term of this bracket, plus the first term of this bracket times the second term of this bracket, and then the second term of this bracket times the first term of this bracket, plus the second term of this bracket times the second term of this bracket. So in this case, it would be 1 times 6, 6, plus 1 times 2i, 2i, plus I times 6, 6i, plus I times 2i, 2i squared. Now, the thing you have to look out for here, before we simplify this, is this I squared term right here, because we know that I is equal to the square root of minus 1. So I squared is going to be minus 1. And I can sub that into my equation here. So it's like I have 6 plus 2i plus 6i plus 2 times minus 1. And now if I group the real parts and the imaginary parts, I'm going to get 6 minus 2 is 4, plus 2i plus 6i is 8i. Two cases for division of a complex number. In this case here, the first case, I have a complex number divided by a real number. And here, if I just write this out like this, 3 plus 9i is my complex number in this case, divided by 3. This is the same thing as these real parts divided by this number on bottom, plus this coefficient of the imaginary part divided by this number on bottom. So I get 3 over 3 plus 9i over 3, which simplifies to 3 over 3 is 1, plus 9 over 3 is 3i. In the second case, I'll be dividing a complex number by another complex number, and to do this, I use something called the complex conjugate of the number on bottom. The complex conjugate of a complex number in the form a plus bi is just a minus bi. That's it, I just changed the sign in front of the imaginary part. And how this applies to division here is that I can write this is the same thing as 2 plus 3i over 4 minus I times complex conjugate of what's on bottom. So in this case, that's 4 plus I over 4 plus I. And this will give me terms which are easier to simplify. The reason I'm allowed to do this is because anything divided by itself is equal to 1. So this is basically the same thing as multiplying this whole expression by 1, because see, I have 4 plus I on top and 4 plus I on bottom. Now my rules for fractions show me that this multiplication is just going to be the top parts times the top parts and the bottom parts times the bottom parts. So I'm going to get 2 plus 3i times 4 plus I divided by 4 minus I times 4 plus I. And I'll expand all these terms out to show how it simplifies. So I get 2 by 4, 8, plus 2 by I, 2i, plus 3i by 4, it's 12i, plus 3i plus I is 3i squared. Remember, same trick with this I squared, it's always just equal to minus 1. And this is divided by 4 by 4, 16, 4i is 4i, minus I times 4, minus 4i, minus I times I is minus I squared. And to simplify this again before we move on, plus 4i and minus 4i are going to cancel out. This I squared term is going to turn into minus 1, and minus minus 1 is plus 1. So this on bottom is going to be 16 plus 1 is minus times a minus is a plus. And this I squared term here is also going to be minus 1. And now if I just add all the like terms, I'll get 8 minus 3 is 5, plus 2 plus 12i is 14i, over 16 plus 1 is 17. Now if I remember my first case here, I can also write this as each of these terms divided by what's on bottom. So my final answer is 5 over 17 plus 14i over 17. To solve an equality involving a complex number, you need to understand that if one complex number, say a plus bi, is equal to another complex number, say 2 plus 3i, then the real parts and the coefficients of I must also be equal. So in this case, a is going to be equal to 2, and b is going to be equal to 3. This can get more complicated in expressions such as this, where I have this complex number is equal to this complex number, and I'm told to find x and y. But this works just like the example here, where the real parts are going to equal the real parts, and the imaginary parts are going to equal the imaginary parts. So if I want to equate my real parts, I'm going to look through this for everything that doesn't have an I. So on this left-hand side, I have x plus 1 plus 3i. So on the left, I'm going to get x plus 1. And on the right-hand side, I have 3 plus y plus 1i. Well, this y plus 1 is all times I, so all I have as a real part here is 3. And to get x in this case, I can just take away 1 from both sides and get that x is equal to 2. Now I've found x, and to find y, we're going to do the same thing with these imaginary parts. What do I have on the left with an I term? It's going to be 3, because I can just take the coefficients, remember? And this is equal to all the coefficients of I on this side is y plus 1. And here I can again just take away 1 from both sides, and I'm going to get that y is also equal to 2. Now I have found x and y. There's another type of equality which is even more complicated, so I've written out the steps here in case you want to pause the video and go back and try to solve it yourself. So I'm given the square root of negative 12 take away 16i is equal to a plus bi. And in this case, I should have written that a and b are both, are both real numbers, because that'll come in handy later. Now first, I'm going to square both sides to give me that minus 12 minus 16i is equal to a plus bi squared. Now I'm going to try and simplify whatever's on the right-hand side. So a plus bi times a plus bi. Remember, that's the same as a plus bi squared. And if I write this out here, I will get a by a squared, a plus a times bi is abi, bi times a, also abi, bi times bi is b squared, I squared. Now I'm going to try and simplify so that I have all my imaginary and real parts are easy to see. I'm going to have a squared here, and this b squared term is times I squared, so I squared, remember, is equal to minus 1. So I'm going to get minus b squared plus abi plus abi is 2abi, because I have 2 of them. And now I have this equality in a form that I can see that these real parts are here, and these real parts are here, and they're equal, and that these coefficients of I and these coefficients of I are also equal. How I find a and b from here is just like in the last example. I'm going to equate these real parts and these imaginary parts. So I'm going to get 2 different equations. Minus 12 is equal to a squared minus b squared, and minus 16 is equal to 2ab. I'm going to look at these 2 equations that I have now, and I'm going to see which one has the easier variable to isolate. And in this case, it's this one because it doesn't have any square terms. And I'm going to get that a is equal to minus 16 divide both sides by 2b divided by 2b, because that's how I want to get a on its own, just divide out by this number here and this one here. And I'm going to take this a is equal to minus 16 over 2b, and I'm going to sub this in to the a term I have over here, and I'm going to solve this equation for b using that. So now that I know what a is, I'm going to get minus 12 is equal to minus 16 over 2b squared minus b squared. And let's try simplify this some more. Negative 12 is equal to minus 16 over 2b is the same as minus 8 over b, because I can just divide out by 2 here, and all this squared, minus b squared, which then is equal to minus 8 squared over b squared minus b squared, because we know from algebra that if we have some number divided by another number to some power n, then that's the same thing as the number on top to the power of n divided by the number on bottom to the power of n. And we just use that here to get this. Now, what else can I do to simplify this equation? Well, negative 8 squared is going to be 64 over b squared minus b squared. And I don't want to deal with this fraction anymore, so I'm going to multiply everything in my equation by b squared. So what I get next when I multiply everything here by b squared is I get minus 12 times b squared. And remember, we're working out this equation here. So I get minus 12 times b squared is equal to 64 divided by b squared times b squared is going to be 64 minus b squared times b squared, b to the power of 4. And I can rearrange this again and get that minus b to the power of 4 plus, well, b squared plus 64 is equal to 0. Now I'm going to factorize this expression and I'm going to get two quadratic equations. So I'm going to have that minus b squared here plus something else times b squared here plus something else equals 0. Now I can look at all my factors of 64, which when added are going to get 12. So I can write 64 up here, and I can think of my factors. Well, it would be 32 times 2, and well, I don't see how that could become 12. What about 16 times 4? Well, this is going to work because I have this minus number here, which means that if I have 16 right here, then this added to minus 1 times the outside number 4 has to equal 12, which it does. Now I have two separate quadratics, which I can try and solve for b. I have that minus b squared plus 16 is equal to 0, and I have that b squared plus 4 is equal to 0. Now I can rearrange these to get b. So let's start off with this one on top. Minus b squared would be equal to minus 16. That's taking 16 out from both sides. And I can multiply this all by minus 1, and it'll be the same as b squared is equal to 16. So b could be the square root of 16, which could be plus or minus 4. What about my other equation here? Could these be the solutions? Well, let me try this. B squared is equal to, I'm going to take away 4 from both sides, minus 4. So B is equal to the square root of minus 4. But wait, remember I said at the beginning that A and B both have to be real numbers? The square root of a negative number is not included in real numbers, so it can't be this. It has to be this one here. So now I have two values for B, and I can use those to solve for A. I already have an expression for A, if you remember. All the way up here, I said that A was equal to minus 16 over 2B, or minus 8 over B. So I'm going to write out my two solutions here. Solutions. When B is equal to 4, A is equal to minus 8 over 4, subbing in for B here. So A is minus 2. And when B is equal to minus 4, then A is equal to, remember from up here, minus 8 over minus 4 is equal to positive 2. Now I have my solutions for a and b, and I can write this in just one more way. I can write that the square root of negative 12 take away 16i is equal to this complex number with a is 2 and b is minus 4, or this complex number where a is minus 2 and b is 4. An argand diagram is a way you can visually represent your complex number. To get an argand diagram, I draw an x-axis and I put the real part of my complex number here, and then I draw a y-axis and I put the imaginary part of my complex number here. For example, if I'm given that z is equal to 4 minus I, then I go out here to 4 units, which say that's here on my real axis, and I go down by 1 to minus 1 on my imaginary axis, and z, my complex number, would be right here. Let's do another one. So say I have z is equal to 2 plus 6i. Then I'm going to go to 2 on my real axis and 6 on my imaginary axis, wherever that would be, because I plot my imaginary parts here on the y-axis and my real parts on the x-axis. And then I would go up and plot z2, let's call it, right here. The distance from the origin to the point is called the modulus, and you get it using this formula here, where x is my real part and y is the coefficient of my imaginary number here. So say I want to find the modulus of z2, which would be this distance here. I would say that r is equal to the square root of the x part, which in this case is 2 squared, plus my y in this case, I go up the y-axis and I get 6. So we're using this complex number here, 2 plus 6i. I get 6 squared. And then this distance here, this we're calling r, it's going to be the square root of 4 plus 36. It's going to be the square root of 40. And maybe I should have picked a nicer number here, but that is this distance from the origin to my point. Now let's look at some of the translations which will happen to your point when you add another complex number to it. Here I've given myself z1, z2, and z3. I plotted them here and told myself to add z4, this number, to each of these points and see what happens. So I have z1 is equal to 1 plus 2i, and z2 is equal to 2 plus 3i. So z1 plus z4 is going to be real parts and imaginary parts. 3 plus 5i. We can go in now and plot this result. So about 3 on the real axis here, and 5 on my y-axis is going to be, say, around here. So the result is going to end up somewhere here. And we can see that adding another complex number to z1 has resulted in a translation of the point. z2 is equal to 2 plus I. So for my second problem, I'm going to do 2 plus I plus 2 plus 3i. Add these up and I'll get 4 plus 4i. And when I plot this result by going out 4 units on the x-axis and up 4 on the y-axis, I'm going to end up around here. And if you look at this, if we had maybe more accurate graph paper, we can see that z1 and z2, when we add the same number to these points, they translate by the same amount and in the same direction. Our third problem, we have z3 is equal to 2 plus 2i. So 2 plus 2i plus 2 plus 3i is going to be 4 plus 5i. And again, we can plot this. We can go out 4 for the real part and 5 for the imaginary part, and this point will be around here. Now we can see that because all of these points, when we add the same complex number to them, they translate by the same amount. So this kind of triangle shape between my original points has been maintained. It's just like the shape has moved in the plane. But what translation will our point undergo if we multiply it by a constant or a real number? So we're told to plot 2z. So 2z is going to be equal to 2 times whatever's in z is 2 plus 4i. So we're going to get 4 plus 8i. Now we can plot the result. We get 4 and 8. I'm going to say it's around here. And my 2z is going to be maybe here. This shows that my point has moved away from the origin by a factor of 2. Which seems obvious enough, but what about when we multiply z by 1/2? So 1/2 of z is going to be half of 2 plus half of 4i. It's going to be 1 plus 2i. And again, if I plot this result, I'm going to get 1 and 2, and it's going to be about here. And now z has translated in towards the origin by, again, a factor of whatever this constant term is here, of whatever this real number I'm multiplying by is here. So it's moved in by a half towards the origin. My last problem here asks me to plot minus 1z. Minus 1z is going to be minus 1 times 2 plus minus 1 times 4i. So it's going to be minus 2 minus 4i. So I'm going to go to minus 2 on my x-axis and minus 4 on my y-axis, which is about here. This is where I get minus z. And from this I can see that it's the same distance from the origin as z. It's just reflected across the origin like this. See, if there's a mirror along this dotted line, then these two numbers would be reflections of each other. Now it gets interesting. I can see what happens when I multiply this number by I. Z is 3 plus 6i, so that's 3 on my x-axis and 6 on my y-axis. So z goes here to start off with. What about z times I? Zi. Well, this is going to be I times 3 is 3i, plus I times 6 is 6, sorry, I times 6i is 6i squared. And from this, I get minus 6 plus 3i, because I squared is equal to minus 1, remember. It's hard to see the correlation now, but let's do another one. Let's multiply this by I again. So it's like I'm multiplying by I squared. So Z3 is going to be I times minus 6 is minus 6i, plus 3i times I, 3i squared. So I'm going to get minus 6i minus 3, or, well, I guess in the standard form it would be minus 3 minus 6i. And when I go to plot this, I can go to minus 3 on my x-axis and minus 6 on my y-axis. I'm going to find myself around here. This is Z3. Now you might be able to see where I'm going with this, but we're going to do one more and multiply this number by I again. Z4 is going to be minus 3 times I, it's minus 3i, minus 6 times I minus 6i squared, which is going to simplify to minus 3i plus 6, or I guess 6 minus 3i. Now I plot this by going to minus 3 on my x-axis and 6 on my y-axis, and I come out here at Z4. And if I zoom out a bit, so we can see all the points, I'm going to take a circle, and I'm going to draw a circle through all of my points like this. Now this circle represents 360 degrees. So I have here 0 and 360. This circle goes around all 360 degrees. And the relationship between these points is that each multiplication by I gives me a 90-degree turn. So from Z to Z2, that's Z multiplied by I get a 90-degree translation here. And the same goes for every subsequent multiplication by I, results in a 90-degree turn. The conjugate roots theorem says that if you have a polynomial and the root of that polynomial is a complex number, then the conjugate of that complex number will be another one of its roots. We can show this by solving this polynomial here. Let's use the minus b formula, where we have that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, where a is the coefficient of x squared, b is the coefficient of x, and c is the constant. Except because we're using complex numbers, we have z here. We're using z instead of x. To find the roots of this equation, I'm going to write this out. So minus b is the coefficient of x, so 2 plus or minus the square root of 2 squared minus 4, a is 1, and c is 2 divided by 2. Oh, that was a very straight line. It's unlike me to have neat handwriting. Times 2a. A in this case is 1. So this is minus 2 plus or minus the square root of, this is going to be 4, and this is going to be 4 times 1 times 2 is 8. So 4 take away 8 is going to be minus 4 all over 2. I'm going to simplify this third. So this is the same as minus 2 plus or minus the square root of 4 times minus 1. So the square root of 4 times the square root of minus 1, which we know what we're going to do here, like we did earlier. We're going to have that this is all equal to 2 plus or minus 2i, because 2 is the square root of 4, and the square root of minus 1 is I, divided by 2. And now we can just take this 2 out of the equation like this, just dividing out each term. We're going to get minus 1 plus or minus I. And this shows the conjugate roots theorem because minus 1 plus I, let's say that's z, then its conjugate is just going to be minus 1 minus I, which is the other root, and also the conjugate because we changed the sign before the I. A typical kind of question you might be asked about conjugate roots is to show that this here is a root of some polynomial, and then write down the other root. For this first step, to show that this is a root of this here, we're going to write it out with function notation, that f of z is equal to z squared plus 4z plus 20. And we know that f of any root is going to be 0. So we're just going to sub this in here and see if it equals 0 to show that it's a root. So f of minus 2 plus 4i is going to be minus 2 plus 4i squared plus 4 times minus 2 plus 4i plus 20. And this is minus 2 times minus 2 is 4. Minus 2 times 4i is going to be minus 8i. 4i times minus 2 is also minus 8i. And 4i times 4i is 16i squared. 4 times minus 2 is minus 8. 4 times 4i is 16i. and all of this plus 20. Let's simplify this again and see if we can check that it's equal to 0. So this 16i squared turns into minus 16 because it's the same as 16 times minus 1. So we have a minus 16 here. So for our real parts, we have 4 minus 16 minus 8 plus 20. And for our imaginary parts, we have minus 8i and plus 16i. And if we look at this, minus 8 is going to be minus 16i plus 16i, which will cancel out. And 20 minus 8 is going to be 12, and 4 minus 16 is going to be minus 12. So this is all going to cancel out here, and we do get that this is equal to 0. And if you leave out the dashes I've drawn through the numbers here just for clarity, you can then you can give your answer like this, and that is showing that this is a root. Now this part of the question here, write down the other root. This is just very directly the conjugate roots theorem. If z is equal to a plus bi, then its conjugate is a minus bi. So in this case, one of our roots is minus 2 plus 4i. So the other root is going to be minus 2 minus 4i. And this is the other root. The polar form of a complex number is a different way of writing a complex number. To understand how, we're going to look at what we know about coordinates. So if we want to locate a point in the coordinate plane, we have our Cartesian way, which is where we give the length along the x-axis and the length along the y-axis. And now we know that there's only one point, which is this far up the y-axis and this far up the x-axis, and that point is here. And that's how we locate points with Cartesian coordinates. But there's also another way of doing this called polar coordinates, where I take the distance from the origin to that point and also the angle from the x-axis. And so I can locate a point in the plane by knowing these two things, the distance and also the angle. One important thing to know about this angle here is that in the leaving cert, when you're taking the polar form of a complex number, this always needs to be between pi and minus pi. Say if 0 pi was here, then the size of this angle always needs to be between pi and minus pi. There's an easy way to remember this, which is just to always take the angle from the positive x-axis when you're getting polar coordinates for a complex number. So if my point was in the second quadrant, right here, then I'd take my angle like this from the positive x-axis. If it was in the first quadrant, the same. And if it was in the third or fourth quadrant, say this is my angle here, then I would take the angle also from the positive x-axis, like this. Now to get the polar form of a complex number, we have to remember this acronym, which I didn't used to like very much, SOHCAHTOA, which gives us that sine theta is equal to the opposite over the hypotenuse, and cosine theta is equal to adjacent over hypotenuse. So if we imagine that this is a sort of triangle here, then the sine of this angle is going to be my opposite, which is going to equal my y-coordinate because it's this length here, divided by my modulus, which is my hypotenuse if this was like a sort of imaginary triangle here. I can use this to express y if I divide out both sides by r, and I'll get that y is equal to r sine theta. Similarly, for cosine, it's equal to the adjacent divided by the hypotenuse, so the adjacent side along here is going to be my x-coordinate divided by the hypotenuse of this triangle is my modulus here. And again, to solve for x, we're going to multiply by r on both sides, So this becomes x is equal to r cos theta. And because in an argand diagram, I have my real parts on my x-axis and my imaginary parts on my y-axis, then I could write this complex number as the expression for my x-coordinate, which I just figured out here, which is r cos theta. Z is equal to r cos theta plus I times the expression for my y-coordinate, which if I remember was r sine theta. So I or sine theta. And this is how we get the polar coordinates. For any complex number, we factorize out r, and we get that z is equal to r cos theta plus I sine theta. Let's try this. So we have this complex number, 2 plus 2i, and we need to put it in polar form. We need two things. We need r, and we need theta. Because if we look up here, we just need to know two things. We need this r, and we need this theta. Well, we already have a formula for r. It's going to be the modulus x squared plus y squared. And to get theta, generally we look back at this acronym here, SOHCAHTOA, and we use this third one, tan is equal to opposite over adjacent, where the opposite side of this angle is going to be the y-coordinate here, and the adjacent side is the x-coordinate. So I get that tan theta is equal to y over x. So if I want the angle theta, then I use arctan in my calculator on y over x. So if we write this down here, we get theta by using arctan on y over x. And in this case, let's just draw a little argand diagram sketch to kind of visualize this a bit more. Our real part goes along the x-axis, so we have that 2 is our x value, and in this case, 2 is also our y value. So the modulus is going to be r is equal to the square root of 2 squared is 4 plus y squared, 2 squared again, is 4. It's equal to the square root of 8. And our angle theta is going to be equal to arctan of 2 over 2, which if I type that into my calculator, I get pi over 4 radians. And it's good here to make sure this is the correct angle, because the tangent of two angles at 180 degrees to each other are going to be the same, and you need to make sure that the calculator has given you the right angle. So if I draw here on my diagram just a sketch of where my point is, and if pi is here and minus pi is here, then this looks like yes, 1 over 4 pi is right. And then I just go ahead and use my formula for the polar form, which is r cos theta plus I sine theta. And I get that this number z, when in polar form, is going to be equal to the square root of 8 as r times cosine pi over 4 plus I sine pi over 4. And this is polar form. There are formulas for the multiplication and division of complex numbers in polar form, and I'll write these formulas here. If we have one complex number times another complex number, then the product is the modulus of the first times the modulus of the second multiplied by cos theta 1, that's the argument of the first complex number, plus theta 2 plus I sine theta 1 plus theta 2. And for division, if we're asked to divide these complex numbers, then z1 over z2 is going to be the modulus of the first divided by the modulus of the second, the number on bottom, times cosine the argument of the number being divided minus the argument of the number it's being divided by, plus I sine theta 1 minus theta 2. For an example, let's take that z1 is equal to 4 cos pi over 6 plus I sine pi over 6, and z2 is equal to 3 cos pi over 3 plus I sine pi over 3. So using our formula from above, and given that this is in polar form, we know that R1 is 4 and R2 is 3. So our answer is going to be R1 times R2 times cosine of theta 1 plus theta 2, so theta 1, and we can just see this easily because they're in polar form, is pi over 6 plus theta 2, again, we can just see this here and here, is pi over 3, and then plus I sine pi over 6 plus pi over 3. And I can simplify my answer by saying that z1 times z2 is equal to 4 by 3, 12 times cosine of, if I go into my calculator, I can add pi over 6 and pi over 3, and I get pi over 2 plus I sine pi over 6 plus pi over 3, pi over 2. And that's my answer for multiplication. Now let's do one for division. I have two numbers, z1 and z2, and I'm going to divide z1 by z2. So if I look back earlier at my formula that I have for this, I take R1, which is 9, and divide it by R2, which is 6, and multiply this by cos theta 1 minus theta 2. So theta 1 is whatever number's on top. So it's this here, 5 pi over 6, 5 pi over 6, minus theta 2, the argument of the number on bottom, so pi over 3. Then all of this plus I sine the same argument here, minus pi over 3. And then I can put these into my calculator, and this just works out in my head here as 3 over 2 times cos pi over 2. Same as the last case, but that's just coincidence. And then this is all plus I sine pi over 2. De Moivre's theorem gives you a generalized formula for raising z to some power n. So if I have a complex number in polar form, then De Moivre's theorem says that z to the power of n is going to be the modulus raised to the power of n times cos n times theta plus I sine n times theta. I'll go ahead and show this with an example. So here I have that z is equal to 3 cos pi over 10 plus I sine pi over 10, and I'm told to find z to the power of 5. So I'm going to use De Moivre's theorem, and in this case my n is equal to 5. And I can write out that z to the power of 5 is equal to 3 to the power of 5, because remember, 4 to the n from our theorem up here. Actually, I might just move this down somewhere where we can see it while we work. So I have 3 to the power of 5 times cos n theta. So here theta is pi over 10 and n is 5. So I'm going to have 5 pi over 10. That's just 5 times pi over 10 plus I sine 5 pi over 10. And now I can simplify this. So maybe I'll actually just make some space here. This simplifies to 243 times cosine of 5 pi over 10, which is 0. That's just putting my calculator into radians and then typing that in. That's how I figure this out. Plus I times sine 5 pi over 10, which again, I can just plug into my calculator. And I get 1. So this is like I times 1. And then once again, if I simplify here, I get 243 times 0 plus 243 times I. So my answer for z raised to the 5th power is 243i. To prove de Moivre's theorem, we use induction, which we're going to talk about in the proofs video. This is kind of just one of those things you have to like write out 5 times and memorize and then just have it in your brain forever. So we need to show that cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta for any positive integer. So first, we're going to show that this is true for when n equals 1. So we have cos theta plus I sine theta to the power of 1 is equal to cos theta plus I sine theta. And this is true. So we're going to make an assumption of that if n is equal to any k, that this is true also. We're just going to write out cos theta plus I sine theta to the power of k should be equal to cos k theta plus I sine k theta. Now we need to prove that this is true for n is equal to k plus 1. Because if it's true for k being any number and k plus 1, then it's true for every integer number. So we start by writing out cos theta plus I sine theta all to the power of k plus 1 is equal to cos theta plus I sine theta to the power of k times cos theta plus I sine theta. Now we're going to make the assumption that this here is equal to cos k theta plus I sine k theta. And remember, this is all times this here, cos theta plus I sine theta. And now we're going to expand using the distributive law like we did before. We're going to go cos k theta times cos theta. So cos k theta times cos theta plus cos k theta times I sine theta, cos k theta plus I sine, times I sine theta times I sine theta plus I sine theta times cos theta, sine theta, I sine k theta even, my bad, times cos theta plus I sine k theta times I sine theta. plus I squared. That's I squared sine k theta times sine theta. And this I squared becomes a minus 1, so we can just take away this term here. Now we will group the real and imaginary parts to simplify. So we have this cos k theta times cos theta doesn't have an imaginary term, so I'm going to write this here at the front of the equation. And this has an I, this has an I, this doesn't have an I, so we'll put this up here at the beginning. Sine k theta times sine of theta. Now the imaginary parts, we have cos k theta, I sine theta, and I sine k theta cos theta. And this can be written as I times cos k theta sine theta plus sine k theta cos theta. And if I factorize all of this, then I will get that this is equal to cos k plus 1 theta plus I sine k plus 1 theta. And that's the proof. That's it. This is proven here. De Moivre's theorem can be used for some more tricky problems. So here I'm given a complex number and I'm told to find this complex number to the fourth power. But instead of a plus, I have a minus sign in the middle. And for this, I have a slightly modified version of de Moivre's theorem that I just use when I find this minus sign in the middle here. That being that z to the power of n is equal to cosine times minus n theta plus I sine minus n theta. I just change the sign in front of the n here. And now I can evaluate this z to the power of 4. So I have that cosine of negative n, so n is 4 in this case, so negative 4 times pi over 2, that's negative 4 pi over 2, plus I sine minus 4 pi over 2, and I can simplify this to get cosine negative 2 pi plus I sine negative 2 pi, because I've just used this 2 and divided out here and got negative 2 pi as my argument. And then if I want to simplify further, I can type this into my calculator and find cosine of negative 2 pi, which is equal to 1 plus I times sine of negative 2 pi, 0. So in fact, my answer for z to the fourth power in this case is just equal to 1. To solve this, we're going to write out that cosine 2 theta plus I sine 2 theta is equal to cosine theta plus I sine theta squared, because we know this from de Moivre's theorem. And now we're going to expand this bracket out here and then equate the real and the imaginary parts to get sine 2 theta on its own. So for my next line, I'm going to have that cos 2 theta plus I sine 2 theta is equal to cosine theta plus I sine theta times cosine theta plus I sine theta. And if I expand this, I'm going to have cosine theta times cosine theta. So cos squared theta and cosine theta times I sine theta. That goes here. Plus I sine theta times cosine theta. That's another one of these terms. Plus, and I guess I'll have to use a new line here, but it's all the same expression. I squared sine squared theta. And you guessed it, this I squared is -1. So this is actually just minus sine squared theta. Now I'll try and clean everything up. So I have the cosine of 2 theta plus I sine of 2 theta is equal to cos squared theta minus sine squared theta. And this is 2 of the same term here, so I'm just going to have 2 cos theta I sine theta, because I have 2 of them, one here and one here. And now what I want to isolate is sine 2 theta, because that's what was asked. So just like in equalities, I'm going to take all the coefficients of I and I'm going to equate them. So this here, I could even have written this as I outside of 2 cos theta sine theta, just by factorizing. But you don't really need to do that, you just take the coefficients of sine 2 theta is equal to 2 cos theta times sine theta. And this is my answer for finding sine 2 theta in terms of cos theta and sine theta. You might be asked to use de Moivre's theorem to find the nth root of z. So you'll be given that z to the n is equal to some complex number. And we know then that z is equal to that complex number times 1 over n whatever power is given here. So what you do is put this number here into polar form and then use de Moivre's theorem to find that number to the power of 1 over n. Here I'm asked to solve z cubed is equal to 8i. So z is equal to 8i to the power of 1/3. And I'm going to put this 8i into polar form. So for r, I get that the square root of 0 squared plus 8 squared is equal to the square root of 8 squared is just equal to 8. And for my argument, arctan of y over x, well, hang on, I can't do this because x is 0 in this case. So I'm going to draw a little sketch of an argand diagram, and I'm going to plot my number here. Say this is 8, and this is 0. So my complex number is here. And remember that this here is pi radians, and this here is also minus pi. So even though I can't get the value of arctan y over x, I can see from this diagram that this is half of the way to pi. So my argument theta must be pi over 2. And now I write the number out in polar form, which would be the r is 8, so 8 times cosine pi over 2 plus I sine pi over 2. But to get the roots, we need to write this, not just the polar form, but in the general polar form. In the general polar form for a complex number a plus bi is r cos theta plus 2n pi plus I sine theta plus 2n pi. And where this 2n pi figure comes from is because trigonometric functions are periodic. So if this is a cosine wave here, then after 2 pi radians, or 180 degrees, it starts to repeat itself. So I can write this in general polar form by using my OR 8, then writing this out as cosine pi over 2 plus 2n pi plus I sine pi over 2 plus 2n pi. And now I'm going to try and use de Moivre's theorem to find z. So I'm going to write that z is equal to 8 to the power of 1/3 times all of this to the power of 1/3. And this, if I wrote it all out, would give me 8 to the power of 1/3 is 2 times cos 1/3. That's just our n, and this is our argument this time, times pi over 2 plus 2n theta plus I sine 1/3 pi over 2 plus 2n theta. And what's the n in this case? Well, any number, say c to the power of n, has n roots. So we were given z to the power of 3. We're going to get 3 roots. And to do this, we're going to solve this 3 times. First, we're going to sub 0 in for n, then we're going to sub 1, and then 2. And the answers from solving each of those 3 are going to be our answers for z. So let's first take n equals 0 and solve for z. So we have 2 times cos 1 over 3 times pi over 2 plus 2 times 0 times pi plus I sine 1 over 3 pi over 2 plus 2 times 0 pi. And now these terms with the 0, they're all going to multiply by 0 and become nothing. And now we can simplify again, and we're going to get 2 times cosine. This is now all worked out, so we don't need a bracket here. This is 1 over 3 times pi over 2. And if we remember from fractions, it's the tops times the tops and the bottoms times the bottoms. So this is going to be cosine pi over 3 by 2, 6, plus I sine pi over 6. And if I actually type these values in here and solve to get z in the form a plus bi, I'm going to get that z is equal to 2 times cos pi over 6, which is the square root of 3 over 2, plus I times sine pi over 6, which is just 1/2. And this is the same. Now if I distribute 2 as 2 the square root of 3 over 2 plus 2i over 2, which if I just cancel out all these 2's is the same as the square root of 3 plus I. And that is my first root. But like I said earlier, if n equals 3, then I have 3 roots. So now I'm going to let n equal 1 and solve this general form again. So n equals 1, and I'm going to solve 2 cosine 1 over 3 times pi over 2 plus 2 times 1 times pi plus I sine 1/3 pi over 2 plus 2 times 1 times pi. Simplifies again as 2 times cosine of, if I distribute 1/3, I get pi over 6 plus 2 pi over 3 plus I sine pi over 6 plus 2 pi over 3. And if I don't want to do fractions, I can just type these parts here into my calculator. And with that, I get that this is 2 times cosine of 5 pi over 6, then plus I sine 5 pi over 6. Now again, if I want this in the form a plus bi, for the case of n equals 1, then this is going to be 2 times negative the square root of 3 over 2 plus I times 1/2, to which I will get negative 2 the square root of 3 over 2 plus 2I over 2. Then if I just divide out by these 2's, I will get negative the square root of 3 plus I. That is my second root. For my third and final root, I'll be doing this one more time, where n is equal to 2. So if I look up here at my general polar form of the number, I might just copy this to make it faster. So I have the general polar form of the number, and I'm going to sub in n equals 2, get my third and final root. So this here is going to be equal to 2 times cosine 1/3 pi over 2 plus 2 times 2, that's going to be 4 pi, because I sub in my n here, plus I sine 1/3 pi over 2 plus 4 pi. Now simplifying this again, I'm going to get 2 times cosine of distributing this 1/3. It's 1/3 times pi over 2, that's pi over 6, plus 1/3 times 4 pi is 4 pi over 3, plus I sine the same argument here. And now if I give myself a little more space, I can plug these values into my calculator, and I get that cosine of pi over 6 plus 4 pi over 3 is equal to 0. So my first term in the brackets here is going to be 0, plus I times sine of the same, which will give me minus 1. And now if I multiply this one last time, I will get 2 times 0 is 0, plus 2 times negative I is negative 2I. And that's my final root, negative 2I. And our three values of z are negative the square root of 3 plus I, the square root of 3 plus I, and negative 2I. Because this may seem a little complex, we're going to solve one more question. This time, we're asked to find the square root of minus 2 times the square root of 3I. So again, we're going to get this number here into polar form. So my modulus, is going to be minus 2 squared is 4, plus minus 2 times the square root of 3, which is just minus 2 squared times the square root of 3 squared, which is 4 times 3, which is 12. And my value for r here is going to be the square root of 4 plus 12, 16. I'm going to get 4. Now I need to get my argument theta, and easiest way to do that is to draw a little diagram down here under these steps I wrote out. So I know that I want my argument to be between pi and minus pi. And if I look at my real term here, which I'd plot on the x-axis, and my imaginary term here, they're both negative. So I'd go along the negative x-axis and the negative y-axis, and I'd plot this here somewhere in the third quadrant. So the angle that I want is going to be from the positive x-axis to this point here in the third quadrant. And I'm going to have to check that arctan gives me the right angle. So if I just type into my calculator that arctan of y over x is arctan of minus 2 the square root of 3 over minus 2 in this case, and I get the angle pi over 3. Now, does this angle look like it's somewhere in the third quadrant? If my pi is here and all my values between 0 and pi are somewhere here, pi over 3 would be like 1/3 of the way that way. So it would be somewhere around here. And that kind of makes sense if my actual number that I'm working with is in the third quadrant, because they're 180 degrees from each other, and I'd get the same value from taking the tangent from those two angles. But the point is that this is not the angle I need. So what I'm going to do is I'm going to get minus pi, which is all this distance here, and I'm going to add pi over 3. And what I should get is this angle here, taken from the positive x-axis to my point. And when I just punch this into my calculator really quick, I get minus pi plus pi over 3. The value of the angle that I actually want to use is minus 2 pi over 3. And that's my value for theta. So let me write this number now in polar form. So I have my or is equal to 4 times cosine negative 2 pi over 3 plus I sine negative 2 pi over 3. But again, I want this in general polar form, which looks like this. Or times cosine of theta plus 2n pi plus I sine theta plus 2n pi. And then if I sub all these values in here, the general polar form for this number is going to be 4 times cos minus 2 pi over 3 plus 2n pi plus I sine minus 2 pi over 3 plus 2n pi. Now again, to get my roots, I'm going to raise this all to the power of a half, because I'm finding the square root of this number. So using de Moivre's theorem on this would be 4 to the power of a half times cosine of 1/2 times all of this. I'm sure we know the drill by now. And again, we're just going to plug in n equals 0 to get our first root, and n equals 1 to get our second. And we only need to go up to n equals 1 because this is a problem involving the square root, so we only have 2 roots as n equals 2. So the square root of 4 equals 2. So this is 2 times cos of 1/2 times minus 2 pi over 3 plus 2 times 0 pi plus I sine 1/2 times minus 2 pi over 3 plus 2 times 0 pi. Again, that's just me subbing in for n in the general polar form here. So simplifying all of this, I get 2 times cosine of, this all averages out to 0, so it's 1 over 2 times minus 2 pi over 3, which is minus 2 pi over 6, plus I sine minus 2 pi over 6. 2 pi, that should be. Now I can just plug this all into my calculator, and I get 2 times 1/2 plus I times the square root of 3 over 2, which simplifies again to 2 over 2 plus I to the square root of 3 over 2. And if I just divide out by all these 2's, I get 1 plus the square root of 3i. And this is my first root. And actually, just a correction here from later on. This is meant to be I times negative the square root of 3 over 2, which makes this all work out to 1 minus the square root of 3i. And for my second root, just one more thing. I set n is equal to 1, and I sub all these values into my general polar form. So I get cosine of 1/2 of minus 2 pi over 3 plus 2 times 1 times pi plus I sine 1/2 times minus 2 pi over 3 plus 2 with 1 as my n times pi again. So this equals 2 times cosine of 1/2 times minus 2 pi over 3 is equal to minus 2 pi over 6 plus 1/2 of 2 times 1 pi is just 2 pi. So 2 pi over 2, I'm just going to get 1 pi. And I add all this to I sine of minus 2 pi over 6 plus pi. And I can use my calculator to simplify these parts for me. And I get 2 times cosine of this is equal to minus 1/2 plus I times the square root of 3 over 2. And again, if I just divide out by all these 2's, I get -1 plus the square root of 3i. I hope this video has been valuable to you in some way. Thank you for watching.